Imagine for a moment an alien vessel from a distant star streaking through the void of our solar system. It moves with a velocity that bends our understanding of physics, a speed so immense it approaches the ultimate cosmic speed limit. What would the universe look like from their cockpit? How would the fabric of space and the flow of time itself be altered for them? The reality of such a journey is profoundly stranger than anything we experience in our day-to-day lives. Actually, for any object with mass, achieving the speed of light is an insurmountable barrier, a privilege reserved only for massless particles like photons. To accelerate something tangible to that ultimate velocity would require a literally infinite supply of energy. The closer you get, the more astronomical the energy demands become. Even so, we have witnessed matter get tantalizingly close. Scientists have observed some particles traveling at an astonishing 99% of the speed of light. For typical people such as ourselves, there is simply no possibility of ever getting close to these incredible speeds. But if through some extraordinary means you could, the transformations to your perception of space and time would be utterly remarkable. Let's ease into this idea, as it can be quite a difficult concept to wrap your head around. We'll simulate a journey from a complete standstill all the way to moving at nearly the velocity of light. This is a clever little game created by MIT called A Slower Speed of Light, and it illustrates what you would see if the speed of light itself were to gradually slow down, eventually matching a casual walking pace. At this start, my avatar looks around the world and everything appears perfectly normal. But as I start to gather these glowing orbs, the game doesn't make me faster. Instead, it lowers the speed of light, which effectively simulates what it would look like to travel at unbelievable speeds over immense distances. Perceptual changes as light slows. So what becomes noticeable as the speed of light begins to drop? The very first thing I perceive is that colors start to shift. This effect is caused by a phenomenon referred to as the relativistic Doppler effect. You see, the reason you perceive color on an object is that light, which is made of particular wavelengths, is striking your eyes. The longest wavelengths our eyes can register are reds, whereas the shortest are violets. Just beyond our ability to see are infrared and ultraviolet light. However, when you're moving at an incredibly high velocity, the Doppler effect causes some wavelengths that were once invisible in the infrared and ultraviolet spectrums to shift into a range that you can now detect. All at once, things that were previously hidden from sight become visible, like the heat signature of objects in infrared or fluorescent materials in ultraviolet. The faster your velocity, the wider your range of visible light becomes. Light certainly does travel in waves, but it's also composed of a stream of individual particles known as photons. As you accelerate into this stream of oncoming particles, a greater quantity of photons will strike your eyes, making everything in your forward view seem much brighter. In contrast, if you were to look behind you while moving forward, your view would become darker because fewer photons would be able to catch up to you. This is often called the searchlight effect. Time dilation and distorted distances. What other changes do you start to see? You might get the sense that we are progressively moving faster, but in truth, our speed remains perfectly constant for the entire game. We are just walking at the same pace we were at the beginning. This is a direct outcome of special relativity, and more specifically, time dilation. Among the most fundamental principles of the universe is that the speed of light never changes. Space and time, however, are not constant and can indeed be warped. Consequently, when you are in motion, two aspects change from your viewpoint relative to observers who are stationary: your experience of time and your perception of distance. Let me clarify this. For an object that is moving faster, time actually passes more slowly. This isn't just a theory, it has been proven with experiments. If you were to have two clocks with one remaining still and the other moving at high speed, perhaps on a rocket, the time on each clock would slowly fall out of sync. This is the very reason that the clocks aboard satellites orbiting our planet need to be adjusted from time to time, or else they would drift away from the time on Earth-based clocks. It's not a huge amount, just a few milliseconds each year, but these tiny discrepancies would add up over time. The quicker you travel, the more significant time dilation becomes, until at the point you reach the speed of light, the passage of time would effectively stop. This suggests that photons, the particles of light traveling at light speed, experience no passage of time at all. But let's get back to how time dilation affects our experience inside the game. If we remove the lighting effects, we can see this concept much more clearly. Remember, our walking speed in the game never changes. It's the speed of light that gets progressively slower as we gather more orbs. And yet, it truly feels as though we are moving much more swiftly near the end of the game compared to the start. What's taking place here is that our own personal time is flowing more slowly than the time of everything around us. As a consequence, it's as if the distances in space have become shorter, which means we arrive at our destinations faster from our own point of view. In a real-world scenario, this would mean that if we were to travel inside a spaceship moving close to the speed of light for what felt like 1 year to us, it would feel completely normal. For people back on Earth, however, 10 years would have passed. If you were actually able to travel at the speed of light, you could get anywhere in the universe in an instant from your perspective. But on Earth, the distance of your journey in light years would correspond to the same number of years from their point of view. So if you wanted to travel 40 light years away and could move at light speed, you'd get there instantly from your viewpoint. Yet for observers on Earth, you would seem to arrive there 40 years later. Then again, in reality, traveling at the speed of light is impossible for anything constructed from matter. Aberration of light and Lorentz transformation. The last effect is a strange one. It feels as though our field of vision is changing. This is a result of the effects of the aberration of light and the Lorentz transformation. Light requires time to travel to our eyes, so when we look at any object, we are actually seeing that object as it was in the past. Even as you watch this right now, there is an infinitesimally small time lag as light needs a moment to leave your screen and enter your eyes. As we move around in the game, the object we are looking at is no longer in the position where we see it. You might have been thinking while watching this that I must be terrible at video games because I'm constantly running into walls and failing to collect the orbs. But this effect means that I'm not actually standing where I think I am, because the more orbs I have, the slower light is traveling. As a result, I have to start turning a little bit earlier than I'm used to, which is a very difficult thing to get your head around while trying to navigate. It's a lot like playing a game with significant lag. This effect also means that I can see much more of what's around me in a single glance. This animation helps show why the light source is moving relative to me as I move forward. The unseen world of relativity. But because that beam of light takes time to get to me, I am seeing where it was in relation to me in the past. When there are many things to observe all around me, it's as if my field of view expands the faster I go, because I am suddenly seeing all these objects where they were relative to me in the past. Light, space, and time get even more wonderfully weird, but I won't get into that in this episode. All I can say is that I am very glad light seems almost instantaneous for us. This game was a fascinating thought experiment to explore what the world might be like if light we're slow. But it hasn't even touched upon the other genuinely problematic situations, such as Earth continuing to orbit the Sun at its current speed, how all of our electronics would be impacted, and other major problems. On the other hand, our ability to get close to the speed of light would be incredibly useful for crossing enormous distances in very short amounts of time. However, time would still be passing normally for everyone on Earth, which means that traveling anywhere in the universe and coming back might be possible for you. But the Earth you return to would look drastically different, with years, decades, or even millennia having passed, all depending on how far your journey took you. Because of the various effects happening outside your ship, everything would look distorted. Your field of view would be much wider, you'd be able to see a much broader range of light wavelengths, and the area directly ahead of you would be intensely, blindingly bright. So there you have it, a glimpse into how your universe would change if you could approach the speed of light. Time and gravity time on the planet. Mercury passes more slowly than it does here on Earth. A single day on Mercury lasts for 58 Earth days, 15 hours, and 30 minutes. We're able to determine this by looking at Mercury through our telescopes and carefully timing how long it takes for the planet to make one complete spin while it orbits the Sun. However, if we were to take a trip to Mercury and start a timer there, we wouldn't get that same number. This is because time doesn't flow as constantly as you might imagine. Its pace can be altered by speed. The quicker you move, the more slowly time progresses for you, but it can also be altered by gravity, and Mercury is significantly closer to a huge source of gravity in our solar system, the Sun. But just how much does gravity affect time? Could we live for incredibly long lifespans if we all just moved to Mercury? Join me today as we answer this very question and explore the strange and warping world of general relativity and gravitational time dilation. I hope that by the end of this video, I'll have earned your like and subscription. To start, what is time, really? The writer Mark Twain once famously quipped that time is what keeps everything from happening all at once. It separates the events of yesterday from today, and today's events from tomorrow's. As you're sitting here watching this video, you are not doing what you did yesterday or what you will do tomorrow. You are in the present watching this video. You are constantly traveling through time, always moving toward the future at a steady rate of 1 second per second. This is the normal speed for moving through time, and it's shared by you and everyone else on this planet. However, this speed isn't a universal constant, as was discovered by Albert Einstein. The faster we move through space, the slower our personal time becomes, reaching a point where, if we could somehow move at the speed of light, time for us would stop completely. If we were to travel to an object located 4 light years away from us, to observers here on Earth, it would seem that our journey took 4 years. To us, however, it would feel as if we arrived at our destination in no time at all. While this might sound like science fiction, scientists have confirmed that this phenomenon is very real. They synchronized 2 clocks. One was placed on a plane that flew around the world, increasing its speed for a long time, while the other was left in a stationary place. When they finally returned and compared the 2 clocks, they found that the clock that had traveled faster had indeed measured less time, exactly as general relativity had predicted. Einstein's predictions and the Pound-Rebka experiment. General relativity is a provable fact, but Einstein also predicted that this same effect would happen with gravity. The nearer you are to a large source of gravity, and the more massive that source of gravity is, the more slowly time will pass for you. This prediction was confirmed as correct in 1959 with the Pound-Rebka experiment, during which gamma rays were shot from the top of a tall building to its base, and any changes to the light waves were measured. They discovered that the frequency of the waves increased as they got closer to the Earth, much like cars bunching up in heavy traffic. The peaks of the radiation waves got closer together. Time slowed down, just a tiny bit, for the gamma radiation as it neared the Earth. This effect is powerful enough that satellites must be programmed to compensate for it, because as they get farther away from Earth's gravity, time for them actually moves faster. Without this programming adjustment, their onboard clocks would fall out of sync with our clocks here on Earth, which would create all sorts of problems. And yes, you heard that right. The gravity of our own planet is strong enough to make time slow down for us. So you're probably now thinking, how much faster would my time be passing if I weren't on Earth, or if Earth had no gravity at all? Well, it's all a question of perspective. The flow of time will always seem normal from your own point of view. You won't feel like you are moving slower, though you might notice some strange things happening around you. It is the external observer who has to deal with your apparent slowdown. Calculating time dilation. To figure out a precise answer to the question, Einstein developed the following equation. We're going to be using this equation quite a bit for the rest of this video, so let's try to understand it. It might look a little intimidating, but it's not as complicated as it appears. T Arjo is the answer we are looking for. How much time would pass on the object we are focused on, which in this case is Earth. TF is how much time would pass in a place with absolutely no influence from gravity. A place like this doesn't actually exist, by the way, but it works as our theoretical stationary clock. G is the gravitational constant, a number that is essentially added to make the math work out. We aren't going to worry about where it comes from. All we need to know is that it is always this specific value. And don't worry too much about the metric at the end. M is the mass, specifically the mass of the object that is creating the gravity. R is the radius, or the distance from the center of that object, and C is the speed of light, a value we know is about 300 million meters per second. So, to figure out how much slower time moves on Earth compared to a location without gravity, all we require is the mass of the Earth and our distance from its center, and then we can choose how much time we want to compare. Just to get comfortable with it, I decided to try this formula using 60 seconds. If 60 seconds go by in our gravity-free zone, how much time passes on Earth? I plugged in the numbers and got our answer. For every 60 seconds that pass, people on Earth only experience 59.996 seconds. To put it another way, 6 billion seconds would have to pass before we notice a difference of 4 seconds. This happens roughly once every 190 years. So in reality, you will only gain about 2 seconds over your entire lifespan because of Earth's gravity when compared to a place with no gravity. That's a little underwhelming. However, we here on Earth are not just influenced by our planet's gravity. We are also under the influence of the Sun's gravity, which, according to our equation, is considerably more powerful. So let's try this again by plugging the mass of the Sun and our distance from it into the equation. This gives us a new number. How much time passes for us on Earth for every 60 seconds of real time that go by? 59.999994 seconds. While that is a bigger number, it still means that you are only seeing a 1 second difference about once every 3 years or so, or in other words, roughly 24 seconds over an average human lifetime. But Mercury is much, much closer to the Sun. Surely time is altered significantly there compared to Earth, with a colossal object like the Sun so close by. How much more does time slow down for us on Mercury? The equation is pretty much the same as before. The only new figure we need is the distance between the Sun and Mercury. The answer to our final question of how much time passes on Mercury for every 60 seconds is 59.99999 seconds. 60 million seconds have to pass before there's even a single second of difference. This takes place about once every 1.9 years, which, when scaled up over a lifetime, comes to about a 38-second difference, only 14 seconds more than on Earth. Black holes and the fabric of time. But from your own viewpoint, you are not actually gaining those seconds because, from your perspective, time would feel like it was moving normally. It would be the Earth that appears to be moving just a tiny bit faster from your vantage point. So if you pointed a telescope at Earth, you would witness 14 more seconds of Earth's history than you would if you were living on it. Since Mercury is a pretty inhospitable place, this is probably not worth the trip. So, does Mercury's closeness to the Sun make time move more slowly for you compared to Earth? Yes, but only by a difference of about 14 seconds over your entire life. In reality, time dilation from gravity isn't actually that dramatic, at least not here in our own solar system. The mass of the Sun just isn't great enough to really stretch time that much for us, even if we were as close to it as Mercury is. The Sun would need to be millions of times more massive before we would start to feel time dilation in any meaningful way. Nevertheless, it still gives us a fascinating look into the way time flows in our universe, and shows us that time is not nearly as constant as we might think. And of course, this leads to one last question. Are there objects in the universe that are massive enough for us to experience significant time dilation around them? There are, and this is where things begin to get very noticeable for an outside observer. At the cores of galaxies, there are objects called supermassive black holes. These objects have masses that are millions to billions of times the mass of our own Sun. In other words, if you were to fall toward one of them, time for you could slow down so much that it would nearly stop. If you were to get close enough to one of these massive entities and then manage to escape, you could spend half an hour in its vicinity and come out to find that hundreds of years had gone by for the people back on Earth. People on Earth with a powerful enough telescope would see you barely moving at all. Even your breaths would take days to complete. In fact, there would be a point right at the edge of such an object where, as you got closer, your time would hit zero. What would happen if you went past that point? Our equations fall apart and therefore cannot tell us what is beyond that horizon. Science doesn't have the answer yet, though there are certainly many theories. But that might be a better topic for another video. General and special relativity can be very confusing subjects, but was this video helpful in assisting you to understand this topic, and is this something you would like to learn more about? Let me know in the comments below, and if you found the video valuable, please think about giving it a like and subscribing. What is time? What is time exactly? On this channel, we have talked about time quite often. We've learned that as black holes warp the space around them, time slows down. We've discovered the time-bending effects of gravity and even how the James Webb Telescope is able to look through time into the distant past by taking advantage of the constant speed of light. All of this makes a certain logical sense. But what is time itself? You can't taste it, you can't touch it, you can't feel it, yet time has an unstoppable grip on all of us, pushing us forward whether we want it to or not. Doesn't something that affects every part of our lives deserve a little more understanding? While this is a field where scientists have many different theories, today I want to share with you one particular model that might help you better understand this mysterious concept that is always ticking away around us. By the end of this video, we're going to have a plausible model for why time slows down when velocity increases and why shapes seem to distort when they experience speeds close to the speed of light. This video is a collaboration with my brother, built upon recognized scientific theory, where we have taken scientific ideas and woven them together into something you may not have seen before. But before we get started, we have to begin with one foundational concept. Time is actually another dimension. Now, before you check to make sure you haven't accidentally clicked on some science fiction channel, let's talk about what I mean by dimensions. While in pop culture, different dimensions are often shown as parallel worlds that are a lot like our own, but with subtle differences, in this context, when we talk about different dimensions, we mean the dimensions of space, as in three-dimensional space or 3D space, which you are likely much more familiar with. This is not a trivial point, however. 3D space is all around you. It is the around you, and is very important to our discussion. Let's start by making sure we have a solid grasp of the three dimensions and the relationships they share, before we bring in the fourth dimension. Generally speaking, 3D, or three-dimensional space, just means a space that can be measured in three different directions that are perpendicular to each other. The perpendicular aspect of these dimensions is very important, but we'll get to that later. Three-dimensional space is usually described as having height, width, and depth, and they all exist at 90-degree angles to one another. To put it simply, objects like us that exist in 3D space are able to move left and right, up and down, and forwards and backwards. We are very comfortable in this kind of space. Using this as our starting point, it becomes much easier to imagine what we mean by 2D space and even 1D space. Visualizing dimensions. To move from one space to another, all we have to do is either take away or add an extra dimension of measurement or movement that has to be at a 90-degree angle from all the other existing angles. So, 2D objects can move on a flat plane that is defined by the X and Y directions, or the X and Z directions, or the Y and Z directions, but never all three at the same time. 1D objects can only move along either the X or Y or Z axis. Imagine a person who lived in a 1D world like that. Their whole life would be restricted to moving in one direction or the other. All of their reality would exist either to their left or to their right, and would just look like a single point. They wouldn't be able to move or see in any other direction, and probably couldn't even imagine that such directions existed. Photons zipping by them would only be visible if they happened to enter the single line that made up a 1D person's entire area of existence. Now, adding extra directions for movement is what is needed to go from 1D to 2D to 3D. So, in principle, we can predict what we would need to do if we wanted to jump into 4D, but this is where we hit a problem. While it's easy to draw a line that's perfectly perpendicular to another single line, or to draw another line on top of those that is perpendicular to the previous two lines, how could we possibly draw a fourth line that is perpendicular to all three? Surely that's impossible. Well, within our 3D space, a thing like that is indeed impossible. The best we can manage is to draw approximations. For example, it's possible to draw an approximation of a 3D shape on a 2D piece of paper by doing something like this. These are all two-dimensional lines, but when we look at this, our brain understands that this is a drawing of a 3D shape. So, in a similar way, we could probably do something comparable to show what a 4D object might look like using only 3D lines. Mathematicians have tried to do this, though their creations tend to be a bit confusing. Even though this is mathematically a solid basis for a 4D object, I personally don't feel that my understanding of 4D space is any better for looking at it, so I won't be focusing on it in this video. Time as a fourth dimension. There is some evidence, though, that a fourth direction does exist, and we are all moving along it at this very moment. That fourth direction or dimension is time. Einstein predicted this very connection when he joined space and time into a single unified space-time in his theories of relativity. According to him, time and space are just two parts of the same whole. To me, this connects with the idea of 4D space very well. Just as there is no fundamental difference between the z and the x or y directions, so too would there be no real difference between time and space. If time is just one more direction, even if it's one we can't perceive, then time is critically important. Without time, our 3D space would be frozen. It would be stuck forever in one state, because it's time that gives us the ability to move around within it. But why are we unable to see it? Why can't we just look in the direction of time? To explain this, let's look at the difference between the various dimensional spaces. We see this most clearly when we think about what 2D objects might look like if they were able to move around in 3D space. This is where we start getting into the model. Let's begin by imagining a standard 3D space. But because we eventually want to see all of space and time in a single model, let's cheat a bit. Let's compress all of 3D reality as we understand it into a flat, two-dimensional plane. In this plane, let's call that our XY plane, which we will label as space, and this frees up the Z dimension for time. In this model, all 3D people are now just 2D. A 2D person could exist and go about their life in the plane marked space at the bottom of our chart. However, by moving them upwards on the chart at a constant speed, they are also moving through time. Let's, just for simplicity and convenience, say that the top of our diagram is the future, while the bottom is the past. So the higher up our 2D person travels in this diagram, the older they get. Since we don't seem to have much control over our ability to move through time, let's imagine for a second that our 2D person is traveling upwards at a fixed rate, as if there's some steady force or wind pushing them up towards the future. Sadly, we can't just slow down time for ourselves with willpower, no matter how much we might want to. The speed of causality. However, it's not quite right to say that we can't change it at all. The faster we move through space, the more slowly we move through time. This is one of the core principles of Einstein's relativity. This model can express this idea using the power of vectors. As our 2D person tries to move to their left or their right, their vector of travel shifts. While moving at a set rate, like a sailboat catching a breeze, we can only move as fast as the wind pushes us. So the vector that extends from their front must always stay the same length. To travel the fastest through time, our 2D person has to point their vector completely in the direction of the future or upwards. However, if they want to travel any distance in either direction to their sides, they can only do it by pointing their vector away from their direction of travel. They now have motion in the x direction, but they've done this by sacrificing some of their motion in the z direction. They are moving through space, but at the price of moving a little more slowly through time. If we take this to its logical conclusion, our person has completely turned onto their side and now only has motion in the x direction and none in the z direction. They have velocity in space, but not in time. So I suppose this means our vector represents the speed of causality, or the speed of light. If this is the speed we're talking about, then moving at slow speeds through space would make no noticeable difference in our speed through time. We would have to be going incredibly fast before we started to see anything. The vector would still be pointing mostly upwards. A fascinating result of this model is that from the 2D man's own perspective, nothing fundamental has changed. He has his own view of what reality is. For him, the vector coming out of his chest is still time. The dimensions of the plane he is lying flat on make up his space. To him, it's the rest of the universe that has become a bit strange, but he himself is perfectly fine. However, once he turns back to his original orientation, it becomes obvious that the rest of the universe has moved on without him. The squishing effect. This is more apparent if we bring in a second 2D person. At first, both of our people are not moving in space. Their entire vector is pointed in the direction of time. Nothing particularly unusual seems to be happening so far. However, if our stick figure on the right turns and vectors at nearly the speed of light for a while, and then reorients himself, while the second 2D man on the left just stays put, it becomes clear that our 2D men have not traveled at the same rate through time. Assuming that our two stick figures can still somehow see each other, let's imagine that they somehow project an image of themselves onto the other person's spaceplane. They would immediately see that there is an age difference. The one who journeyed at near the speed of light did not move as quickly through time as the other one who stayed stationary, and is therefore younger. But why do we find this model so compelling? Well, it's because of what those projections would look like during these changes in direction. From the viewpoint of the first stick figure, initially the projection of his friend looks fairly normal. However, as he starts traveling very fast in space, and his vector is pointing in a direction away from time, a 2D shape shows its inherent flatness, and from a head-on view, it changes from this to this. The fast-traveling stick figure seems to flatten, and this effect gets more pronounced the faster he goes, with the flattening happening in his direction of travel. The stick figure who stays still might be amazed at the strange transformation happening to his friend, never understanding that it represents the reorientation of a 2D figure in 3D space. Now, what truly sparks my imagination about this is that this very same thing happens in real life. According to Einstein's theories of relativity, objects that are traveling at incredible speeds in 3D space would appear, to an outside observer, to flatten in their direction of travel. This squishing effect happens exactly in line with this model and is connected to time dilation. However, from the perspective of the person who is actually traveling, they don't flatten at all. Instead, it is the rest of the universe that warps. I talk about this in more detail in another one of my videos, where we can actually see the effects of spatial warping in a computer model. From their perspective, everything would seem to stretch at the edges of their vision, while their destination would appear to be further away, which is, again, what this model would predict. The only difference is that in this model, we are just looking at a 2D object stretching, so the stretch is only in one direction, whereas in real life, it's 3D, which means it stretches in two directions instead. But that is what you might expect as you turn away from our normal 3 dimensions and start pointing yourself away from time, the shape of reality and light's peculiar behavior. But if this is all true, so what? Why does it matter if time is really a direction? Well, then it deepens our understanding of the universe. It also brings up more questions. What is the force that is always pushing us forward in time? Why does it seem like we can never move against it, even though in this model there is no reason a vector couldn't point downwards? In the real world, that just doesn't seem to ever happen. This model also tackles the question of if time is a direction, what is our shape in time? Does part of us stick out into the past or into the future? According to this model, that doesn't happen. We are like flat pancakes in the 4th dimension, pennies that look round when you see them head-on, but show their thinness when they turn away from you. That's a strange thought, but it might just be true. This could explain why we can't see through time. We just don't extend enough in that direction for it to be possible. Your own form might be very different from what you first thought. Of course, this model is just a theory of ours, though we have tried to base it on scientific observations and conventional theory. But what are your thoughts? Does this model help you to make sense of time as a 4th dimension? Please share your ideas in the comments below on the nature of time and what it might actually be. Instead, I hope to explore more strange concepts like this in a new series called The Unseen World, where I plan to explore the shape of the reality that surrounds us. While it is usually invisible to us, the shape and dimensions of the universe can explain why things are the way they are, and I'm excited to explore it with you. If you are interested in it, let me know. If there's one thing I have come to learn about light, it's that for unthinking energy, light seems to take pleasure in confusing us. For many years, scientists argued about whether it was a particle or a wave because it consistently shows properties of both, seemingly unable to make up its mind. It acts one way when you are looking at it, but a different way when you're not. But at least its speed is consistent. Light always travels at the speed of light, no matter your frame of reference. That one thing always stays constant. Except, no, it seems the constancy of light speed might not be entirely true either. Light might travel slower than physics would predict in some situations. And no, I'm not just talking about light slowing down in denser materials like glass, though that's what I originally planned for this video to be about. We have an explanation for that. I am saying that in some cases, light appears to follow a path through time and space that has it moving either slower or faster than the speed of light, even when there are no dense materials around. But the truly strange part is that it ends up at the same destination in space and time anyway. Allow me to show you what I mean. Thanks to a new take on the double-slit experiment, I want to show you that your understanding of light is either incomplete or, well, just wrong. The enigma of light-speed light travels at 458 meters per second. According to relativity, this is the only speed that light can have, and curiously, it seems to stick to that number no matter what your frame of reference is. Two people could be moving through space, one at 1% the speed of light and the other at 50% the speed of light. But if they both looked at the same beam of propagating photons, they would see them traveling at the exact same speed. Time and distance would apparently rather warp themselves than let you see anything other than light traveling at the speed of light. Of course, when scientists say this, they are only talking about light moving through a vacuum. We've known for a very long time that as soon as matter gets involved, light gets held up and travels more slowly. Light traveling through air only moves at 297,705,000 meters per second, a full 87,458 meters per second slower than light in a vacuum. Light in water moves at about 225 million meters per second. Light passing through glass has a maximum speed of around 200 million. The reasons for this are fascinating but fairly well understood and definitely not physics breaking. When light moves through matter, its constantly oscillating electromagnetic fields cause the electrons within the matter to start moving like boats bobbing on the water. But since electrons moving up and down also create an electric field, which in turn creates a magnetic field, a second light wave is made by these moving particles that, importantly, overlaps the waves of the original light, though it's one that oscillates at a slightly different speed than the original light. The exact speed difference depends on the material. When two waves cross paths, they interfere with each other. They average out, sometimes interfering constructively to make each other stronger, and sometimes working against each other. So when you add up the grand total of all the crests and troughs of each wave, you actually get a new wave, one that travels at a different speed than the other two, and one that moves slower than the speed of light. Eventually, this propagating wave can reach the edge of the blocking material, and without those electrons interfering anymore, you are left with just the original light again, which is then free to continue on its original path again at its original speed as if nothing ever happened. Slowing down and speeding up, light scientists have had a lot of fun with this idea over the years. Researcher Lena Howe at Harvard in 1999 was able to slow light down to an incredible 61 kilometers per hour by sending it through a cloud of sodium atoms that had been cooled to 1/billionth of a degree above absolute zero. 2 years later, Howe was able to bring the speed of light to a complete stop before warming up the cloud and sending it on its way again. You might find that result quite surprising. However, strange things have happened in the other direction as well. In 2000, researchers at the NEC Research Institute in Princeton, New Jersey, sent a pulse of light through a cloud of cesium atoms. Alarmingly, when they tried to see how quickly the pulse came out of the cloud, it looked like it exited before it had even entered. While this might seem to violate causality, how can you leave a building before you go inside after all? Luckily, there was a simple explanation that saved us from creating too many paradoxes. Although the light pulse traveled faster than light, the light itself did not. This was more of an optical trick than a refutation of Einstein's relativity. Let's take a closer look at a photon of light. Each photon is a tiny packet of waves moving up and down. The speed at which the waves inside the packet are propagating is known as its phase velocity, while the speed at which the packet as a whole is moving is known as the group velocity. You can also have a wavefront velocity, which is how fast the very first photon in a wave of photons can travel. This is a bit heavy on the terminology, so let's make it clearer with an example. Think of a crowd of people doing a Mexican wave. The wave that the people are doing is the phase velocity. You can see the wave traveling along through the crowd. It might look like it's moving very fast, but the crowd itself isn't going anywhere, so our wave's real speed is zero. These people make up the group velocity, or maybe the wavefront velocity. Let's imagine that we wanted to send our crowd marching. They could do so, and it could keep doing a Mexican wave as they walked. But even though their waving hands might make the wave go really fast in their direction of travel, it would disappear whenever it got to the front of the crowd. Information exchange couldn't go any faster than the walking speed of the crowd itself, no matter how fast the peaks in the wave seemed to be moving. Einstein, in his theory of relativity, never said that phase velocity couldn't go faster than light speed. He just said that information couldn't travel faster than light. And if you're trying to send a message to someone by sending a crowd of Mexican wavers in their direction, it really doesn't matter how fast they're waving until the first person in the crowd gets there. No information can be sent. Still, this difference between the waves inside light and the speed of light itself will become very interesting in our next experiment. And this is where things start to get a little weird. Oh, you thought it was weird already? Oh no, this is the truly physics-defying part, the double-slit experiment revisited. Let's go back to an experiment we've looked at before, the double-slit experiment. I go into more detail on this experiment in my video here. If you haven't watched it yet, I highly recommend you do, as I'm going to assume you are familiar with what this experiment is about for the next part. This experiment is a fascinating look at how light can sometimes act like a wave and sometimes like a particle. However, in 2023, researchers from Imperial College figured out a way to separate the slits of this experiment, not in space, but in time. The method they used was simple. They took a transparent material called indium tin oxide that, under certain conditions, can be made to be reflective. Indium tin oxide is the material that's used in most mobile phone screens. They fired a laser at it and then very quickly changed the material from transparent to reflective, and then back again. This left only a tiny window, a few femtoseconds long, during which the laser was reflected. They called this a time slit. They recorded what the laser looked like after it had been reflected and found that its frequency had spread out a little in the process, but other than that, nothing too unusual had happened. The strange part was what happened when they sent two laser pulses through these time slits in quick succession. The position of the emitter, the mirror, and the receiver all stayed the same. The only difference was the time the lasers went through. Oddly enough, when two pulses went through, an interference pattern appeared. This was not an interference pattern in the same way as with the regular 3D space double-slit experiment, though. This was an interference pattern that had affected the laser's frequency. Certain frequencies of light within the laser faded out exactly in line with the way intensity faded out in the regular version of the double-slit experiment. Light's path. Through time, to visualize why this might be happening, let's plot this experiment in relation to time. The time-slit experiment can be shown in a similar way to the double-slit experiment, except we are going to need to visualize the change in the experiment over time. To do that, let's make a 4D graph where space is along the x-axis and time is along the y-axis. This is simple enough to do, it just looks like this. The photon leaves the emitter on the left, hits the time slit, is reflected, and arrives at the receiver. I've drawn this as a continuous line just to make things simpler later, but the idea works just as well either way. Later, a second photon is released from the emitter. It reflects and arrives at the receiver at a slightly later time, which is represented by its higher position further into the future on our time graph. If light acted normally, traveling at the speed it was supposed to, this would be the end of it. Instead, light is interfering with itself. This means it must be traveling along a path that takes it through the other slit as well as its own. This is the only way that light could arrive with the pattern that we see, and just like in the double-slit experiment, it's probably happening on the other side of the slits too. As for why it's frequency and not intensity that's being affected here, think about the implications of what you might see if light did indeed arrive at a different angle like this. Photons arrive in small packets of waves, as I've mentioned before. Now, look at what happens if you change the angle at which those waves arrive. Here's how it might normally look. I've added a black timeline here and have highlighted every time the receiver sees a new peak in the wave. Here's what happens when you change the direction of the wave's arrival. Suddenly, the peaks are arriving much more often. The frequency of a wave over time is closely linked to the color we see light as. Lower frequency light is redder in color, while increasing the frequency shifts light's color towards blue. So this color variation makes sense, the unfathomable nature of light. What makes less sense is what is happening with the paths this light is taking through time. Remember that the straight lines we started with represent the 299,792,458 meters per second that we see light traveling. So what can we conclude about the photons that are traveling along these paths? For some parts of their journey, they are moving slower than the speed of light, taking more time to get to a destination that is the same distance away. And yet, for other parts of their journey, they are traveling faster than causality should allow. From their point of view, they are traveling backward in time. As a reminder, these two emitters on the left are actually the same one, just at different points in time, and the same goes for the receivers on the right. It is a mind-bending result, and yet, according to the findings of this experiment done by a research team at Imperial College in London, this is what is happening. The implications of this are astounding. Light always takes the path of least time, the route that lets it get to its destination along the path closest to 299,792,458 meters per second. the fastest anything in the universe can apparently move. And yet, it seems that in its efforts to find out exactly what path that might be, light is testing the waters, sending out feelers that check if other paths, and seemingly other paths through time itself, might be a better solution. These feelers are interfering with photons that travel alongside it, but also with photons that travel a little ahead or behind it in time. To be clear, we never actually see photons taking any of these other paths. We do not see photons arriving from the future. We never see photons traveling slower than the speed of light, as long as there are no supercooling gases to explain why they slow down. And yet, for interference patterns to happen, to at least some degree, light must be trying out alternative routes through time. Maybe it's like lightning testing many different directions to find the best path to its destination before it finds the one that works and collapses down that path in one huge boom, with all the other feelers vanishing and collapsing. Or maybe some other phenomenon is at play. Who can say? For now, all we know is that light has once again shown that it does not follow anyone's rules, at least not rules that we can fully understand. Quantum entanglement and retrocausality. Can information travel backward in time? It's the kind of idea that would be incredibly useful if it were real. You could tell your past self not to eat that burrito that made you feel sick, or you could tell yourself the winning lottery numbers. But it just doesn't happen. The paradoxes that would result alone would make the whole idea ridiculous. In our universe, time always seems to flow in one direction, forward. The idea of traveling backward in time, or even just talking to your past self, seems so absurd it can't possibly be true. So why is it that at the quantum level, information seems to be doing exactly this? What? You haven't seen particles communicating backward in time. Well, perhaps we need to talk about the strangeness that is quantum mechanics. It is an effect that, if we could understand it, could one day lead to technologies like faster-than-light communication, or even faster-than-light travel, at least if we could somehow harness it. But even if we can't, it offers an undeniably strange insight into the unseen world all around us. You're about to see some real-world experiments that are mind-bendingly weird, and if by the end of this video you enjoyed what you learned, feel free to give this video a like and subscribe to the channel. Just please don't break causality when you do it. What do I mean by particles traveling backward in time? By all measures, it doesn't seem possible. In previous videos, I've mentioned that objects would need infinite energy just to move fast enough to reach the speed of light. So how could something move so fast as to reverse the normal direction of time and get to a destination not just instantly, but before it left? Not even light can do that, and it's the fastest thing we know of. Well, this rule about nothing traveling faster than light is mostly true for the macro-scale universe that we live in, and by macro-scale, I mean everything much larger than an atom. But physicist John Stuart Bell noticed an exception to this rule when it comes to quantum entangled particles, the Bell experiment and hidden variables. Okay, so let's start there. What is a quantum entangled particle? In quantum physics, it's possible to collide two particles in a way that links them together, so that by measuring one particle, you learn something about the other. For instance, if you know that the particles originally had a total of 0 momentum, and you find out the momentum of one of the newly quantum entangled particles, you know the momentum of the other particle will be the exact opposite, making sure the total stays at 0. In effect, by measuring one particle, you can learn things about the other. This also applies to other particle properties, like position, polarization, or spin. On the surface, there's nothing too strange about this. It's no different from me meeting up with a friend and talking about our plans for the evening. We agree to go out, and we agree that I will pay for everything for the evening, and my friend will not. Then, no matter how far we go on our night out, or even if at some point we split up, I know I will be paying, and my friend will know that he won't be. This is how Einstein thought it worked. Only it turned out that Einstein was wrong because, as it happens, my friend and I did not talk about who would be paying beforehand, and strangest of all, we still both agree with each other anyway, 100% of the time, no matter how far apart we are. This is the strange part of quantum entanglement and quantum physics in general. We usually think of particles as having fixed properties. However, our first mind-bending experiment shows that particles only have properties when you detect those properties. Until then, they're a bit vague about the whole properties thing, instead relying only on probabilities as defined by a quantum wave equation. This doesn't make intuitive sense. Looking at something shouldn't be what gives it its properties, right? Well, how would you know if a tree falls in the woods, does it make a sound? According to quantum physics, not necessarily. Unveiling quantum spin. Let's talk about the first mind-bending experiment, the Bell experiment. The math for this is quite complex, but stay with me. It's worth the journey. The experiment was first thought up by John Stuart Bell, who wanted to find out if particles really had secret properties that they carried with them, known as hidden variables, or if they were truly making some of it up on the spot. He noticed an interesting mathematical fact about the spin of particles. Before we go on, I should probably explain that quantum spin is not the same as normal spin. Misleadingly, quantum spin actually defines whether a particle is affected, pushed, or pulled by a magnetic field. The name isn't important, but it is crucial to know that these particles aren't actually spinning and so can have different spin values in almost any given direction. Now let's take two quantum entangled particles, and let's say we've set it up so that their spin adds up to a total of 0 between them. This means that if one particle were to be pulled by a field, the other will be pushed by it an equal amount along that direction, with the understanding that this doesn't tell us anything about their spin in other directions. One of the features of quantum spin is that if we measure an entangled particle's spin in any given direction, let's say up and down, it will have a 50% chance to be spinning up and an equal 50% chance to be spinning down. But remember, once you measure the other entangled particle, it will have a 100% chance to be spinning in the opposite direction to the first particle. Based on this fact alone, there's no way to tell if the two particles already knew their spin or are somehow deciding it on the spot and talking with each other now that they've been asked. But Bell noticed a clever thing by asking a clever question. If you measured two quantum entangled particles from two randomly chosen directions, what are the odds that their spin for different directions would be the same? Now let's define that at any time a particle is spinning toward a detector, its spin is up, and any time it is spinning away from a detector, its spin is down. What are the odds that both particles would be spinning up, up, or down, down when tested, and what are the odds that they would be different? The unpredictable quantum world. Let's make this official with a small experiment. Here we have two entangled particles with three detectors reading their spin in different directions. If particle A and B are both red with the top detector, then one of their spins will be up and the other will be down. They are entangled. This is what we looked at before. However, if particle A is red using the top detector, while particle B is red with one of the other two, these two directions of spin are not opposites, so particle B has flexibility in which way it goes. Quantum physics says the particles are making up their attributes on the spot, so once you'd measured the spin of particle A using the top detector, it was a 50-50 chance whether the spin on the other particle using one of the other detectors would match or be different. But this is not what classical physics predicted. Let me show you what I mean. Classical physics claims that particles each carry around secret information that defines their spin in any given direction. So, for our 3 tested directions, each particle would already have a value. They aren't making it up on the spot. Let's say, hypothetically, our particle's hidden information says up-down for particle A and down-up for particle B, as B must be opposite to A for each of the directions 1, 2, and 3. Let's pick a random detector for A. We choose detector 1. Detector 1 tells us that A is spinning up. Now let's pick a random detector for particle B. We pick one there too. This detector gives us a reading of down. 1, 1, up, down. We can actually map out all the possible outcomes of this process of random selection in the graph. There are 9 possible outcomes if you were to only measure from 2 detectors at a given time. 1 to 1, 2 to 1, 1 to 3, 2 2, 1 2, 2 1, 2 2, and so on. For each of these possible selections, we have fixed hidden variable results that we already know because we hypothetically defined them earlier. Let's fill them in now. Of course, if you detect particles using the same detector on both particles, you'll get a different result because they're entangled. But we are not interested in these results. Classical physics and quantum physics both agree on this. So let's take them out. What are the odds that 2 different detectors for particle A and B will give the same result? And what are the odds they'll be different? Remember, quantum physics expected it to be 50-50. Particles are spontaneously creating their values, and so it's perfectly random which they'll pick as they aren't limited by the opposite rule here. But in this table, classical physics says that different results only happen a third of the time. The other times, they're either both up or both down. If we repeat this many times, giving different directions each time and ignoring exceptions, for instance, where the spins of the particles are all up, up, or down, 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 once you crunch the numbers, the important takeaway from all of this is that according to the math, classical physics predicts a matching outcome 55% of the time, while quantum physics continues to just predict 50%, despite the appealing table. This percentage difference was the key. By quantumly entangling particles and doing this test over and over, you could now find out which percentage was correct. And it turned out the winner was quantum physics. Particles were seemingly making up their spin results on the spot, which is unsettling because not only does that call into question our perceptions of reality itself, but it also means that the moment one particle decided on its spin result, its quantum entangled partner instantly knew that that decision had been made. You could test both particles at the same time, no matter the distance, and this same result would be returned. Somehow, information had traveled from one particle to the other in no time at all, much faster than light itself. So, something strange was already happening here. This result disproved Einstein's predictions and showed that some information does seem to travel faster than light. The delayed choice experiment. But we can take this one step further and have information moving backward in time. There is another experiment known as the delayed choice test. Its main goal was to explore the fundamental nature of light, whether it was a wave or a particle, and to find out when it decided to be one or the other. Experiments like the double-slit experiment had done this in the past with mixed results. Sometimes light acted in a wave-like way, creating interference patterns on detectors that could only happen if a wave was interfering with itself. But sometimes it acted like a particle, hitting only a single point on a detector. Most baffling of all, it seemed to change which it acted like depending on whether you were watching its path through space or not. If it could travel multiple paths, and no one was watching to see which it did travel, light simply went through both, like a wave. But when watched, it went through just one, like a particle. This result was baffling enough and deserves a video all on its own. But in 2006, a number of scientists took it one step further by asking an interesting question. What would happen if you tried to watch the light after it had to pick a path? Think about this experiment. A single photon is sent into a beam splitter with a 50-50 chance of either being allowed to continue on its way along path 1 or being reflected upward along path 2. Once on either path, the photon is bounced off mirrors, with both paths coming back together here, where the other beam splitter is put. Once again, the photon has a 50-50 chance to go either way, with an even chance of arriving at one of the two detectors. If light were just a particle, sending a single photon into this experiment would give you an even chance of it arriving at one detector or the other. You'd not be able to tell which way it went, as the two beam splitters make that impossible to know, but you could see where it ended up. However, this does not happen when the second beam splitter is there. The light makes an interference pattern showing that the single photon went down both paths, eventually bumping into itself before moving on to both detectors. This seems like strong evidence that light is a wave. It certainly acts like one here. But what happens if you take out the second beam splitter? Suddenly, you know which path the light traveled down. If light gets to the top detector, it must have come from path 1. If it gets to the side detector, it must have come along path 2. And something about this knowledge spooks the light. It stops going down both paths, and suddenly, each photon only arrives at one detector. The enigma of quantum causality. Here's the critical question. What happens if you put in the beam splitter after the photon has already started down either one or both routes? This is why the test is called delayed choice. If you delay choosing how exactly you plan to detect the photon, whether by knowing which path it came down or making that ambiguous to you, what happens to the light? What happens is a very strange thing. When this experiment was done, it was done many times with the beam splitter randomly being put in or not, but always being put in after the photon had entered one or both paths, and yet the results came back without a doubt. If the beam splitter was there, the photon suddenly and seemingly retroactively stopped picking a path. If the beam splitter was taken out, the photon seemingly knew it would later be detected and picked a specific path to accommodate. Somehow the beam splitter being added or removed in the future changed what the photon did in the past. So, what is happening here? Is it really true that particles somehow saw the future? Did the experiment cause information to be sent back into the past? Or is there some other principle at play here that explains this whole phenomenon, that accounts for the instant transmission of information between quantum particles and allows it to be perfectly rational, that light could travel down one path or both at the same time? Personally, I'm inclined to believe that this is more probable. We clearly do not understand what is happening here, but it must be admitted that if we don't understand what is happening, there's nothing to say that causality isn't being ignored in some way. Perhaps on the quantum level, time really is more fluid than it is up here in the larger universe. Perhaps space and time simply do not apply down there. And perhaps one day someone will be able to come up with a theory that allows all these strange phenomena to finally make some sense. Until then, we'll just have to keep asking the same question. Can information travel backwards in time? Until then, we'll just have to all agree on one thing. Quantum physics is strange.